So my name is Lorenzo Sala. I'm from the University of Trento in Italy. And of course, I'd like to thank the organizers of the LISA Symposium for inviting me to talk about these topics. And indeed, this is a talk not just about one topic, but let's say about two topics that are indeed related. And these topics are the latest results from the LISA Pathfinder mission, from the analysis on the acceleration noise performance of LISA Pathfinder, and about the LISA gravitational reference system. And we will see in a while what. Yes. Okay, and so two things are actually crucial for the LISA measurement. I know this has already been shown yesterday in some way, but I will say it again. And we have to be able to reach the goal of LISA, we have to be able to put test masses in space in free fall. And we have to be able to measure their distance with high precision. And the system that is in charge of addressing this second task, that is the displacement, is the IDS, that is the interferometric detection system. And the LISA system that is in charge of addressing the free fall part is the GRS, and this gravitational reference system. That is what I'm going to talk about now. And so talking about free fall indeed means talking about forces. As you know, in general relativity, any force that would act on a test mass would deviate it from its geodesic motion, and so would show up as a noise. A noise that in the LISA sensitivity curve would show up as a low frequency noise, and as you see here. So we have to control the forces in the end. And many sources can actually generate force on the test masses. Some of them are external to the spacecraft, and once one has overcome these ones, and then there are some other noise sources, some other force sources that are generated within the spacecraft. So in the end, the role of the GRS is to limit all the possible sources of unwanted force below the requirement level, below the level that is actually required to observe gravitational waves. And the level is usually expressed in terms of acceleration noise, of the PSD of the acceleration noise, and we have to be able to set the test masses in free fall at a level that is lower than a few femtometer per second square per root hertz at these millihertz frequencies. And indeed, the GRS is the LISA system with the strongest heritage from the LISA Pathfinder mission, and this is why we are going to talk also about the results from LISA Pathfinder, and also why in these slides all the pictures and all the references regard the LISA Pathfinder mission. So at the very heart of the GRS, there will be the LISA test mass, and the LISA test mass will be surrounded with electrodes. These electrodes serve a double purpose. The first purpose is to control the forces and to control the motion of the test mass, that is applying actuation forces and torques. It is right that along the laser axis, the LISA test mass will not be actuated with forces, but it will along the other 5 degrees of freedom. So that's why audio frequencies voltages will be applied to the test mass to apply forces and torques. And the other things that is done by these electrodes is providing a positioning sensing device that is a positioning sensing that is measuring along all these degrees of freedom. Then the GRS will also provide a test mass charge management system And you know the test mass is free in space, so it's subject to cosmic rays. And whenever the cosmic rays interact with the test mass, they charge it up. And so we need a system to discharge it. And this is done with UV light. And there are also many talks and posters in this LISA symposium about it. Then the GRS is also responsible for the compensation of the gravitational field that is generated by the spacecraft itself to relieve the actuation voltages from applying to great forces. And it's also responsible to set the test mass in free fall, that is launching the test masses with 1 kilonewton of force during launch, and with a locking mechanism, and being able to release them in once on orbit with a velocity that is smaller than a few microns per second. Then the GRS is also responsible of many other things that I cannot list them all now, such as the handling of the vacuum system. This is why you see here the vacuum chambers. And all of this was actually tested on LISA Pathfinder, and a special mention, of course, goes to the magic interferometer of the LISA Pathfinder mission that performed much better than the requirement, and was actually the first sub-picometer local interferometer ever flown in space, and actually made the mission possible. Okay, so now let's move on a bit to the results from LISA Pathfinder. I don't want actually to spend an hour on the introduction of LISA Pathfinder, so I would just say the one sentence that is usually used in this case, and I find it very effective actually. LISA Pathfinder was the shrunk version of LISA, so instead of having an arm length of 2.5 million kilometers, it was just 38 centimeters. So that's the reason why it was basically not sensitive to gravitational waves, but it was indeed very sensitive to noise, to forced noise. And in particular, the main scientific measurement was the differential acceleration between the two test masses that were enclosed in a single spacecraft. And maybe it's, no, I guess it's really well known that LISA Pathfinder exceeded its requirements, its acceleration requirements. You see also the requirements for LISA, and also went down to some more frequencies than it was expected to. And this is actually the famous noise run of February 2017. But we can do something more. We can try and understand what is the origin of this noise, which kind of forces are generating the noise. So first of all, we notice that there are 3 branches. The branch on the right is due to the interferometric readout that actually performed much better than the requirements, and is not actually the focus of this talk. So I will leave it here. And we're going to focus on the 2 branches on the left. So this one that is independent in frequency, and this one that has a fair dependence on frequency with a 1/f amplitude, noise amplitude. And these 2 branches are caused by forces. So we did something more actually, and we went through all the mission, because LISA Pathfinder was a mission that lasted 1 year and a half, kind of. And we looked at how these noises evolved in time. All of these results are in this paper that has just been accepted by PRD. It is now on archive and will soon be on PRD, actually. And so we can start from this one that we call the Brownian noise, and we'll be clear why in a while. And Brownian noise is indeed the manifestation of the residual gas in the vacuum chamber. The vacuum chamber of LISA Pathfinder was opened to space kind of 60 days after launch. And it kept emptying, vacuuming during all the mission. So the thing is that the surfaces in the vacuum chamber emit molecules, and these molecules collide with the test mass, and thus they generate force. They generate a force that is this flat line that I was showing here. It's independent in frequency. And pressure is decreasing during time because the system is vented to space. And then, since the Brownian PSD is proportional to pressure, we expect it to decrease in time. And actually, it is what we measure. Here on the y-axis, you see the PSD of the Brownian noise. And here you see the equivalent water pressure because they are proportional indeed. What we found is that first, the Brownian noise is dominating the noise at the millihertz frequencies, and this is an interesting result for LISA because we see no actual saturation of this noise. And another thing that we notice is that in the end we reached the 2 micropascals pressure at 20 degrees Celsius. And 2 micropascal is the baseline pressure that LISA has to reach after the commissioning phase, after 1.5 years. And another thing that we can understand from this plot is the dependence of the Brownian noise on the temperature. So this is not just a plot of that is showing us the evolution in time. This is also showing us the evolution in temperature. We can treat it like a vacuum system, and we can actually separate the dependence of temperature, and we can rescale data for temperature. As soon as we do it, we see that the data are aligning on a power law, and this power law has some things that are very interesting from the vacuum perspective. One thing is the activation temperature, and the other thing is the exponent of the power law. So we noticed that first, the system is behaving as expected from a vacuum system, but still, this exponent is 0.8, is not exactly 1. I'm saying this because 1 is the exponent that would be expected from emission of water from metal. So we have the conclusion that this is not only water from metal, but maybe this is dominated by some other sources, such as polymers, that were all over the place in the vacuum chamber. So this is another thing that should be kept under control. And after that, we analyzed the stability of the 1/f slope. And so we look at the amplitude of this. We did not expect it to decrease like we did for the Brownian noise, because the origin is not the same, of course. Rather, we noticed that it was remarkably stable over time. You see, over these 500 days of mission, it's changed by just like 20% plus the statistical fluctuations. And another thing that we notice is that there is no apparent trend or evolution in the amplitude of this noise. And we didn't just analyze these frequencies. We also went down further. And we analyzed the very low frequencies that are below the 30 microhertz. We analyzed the 18 microhertz, and we also went down to the quasi-DC. And we noticed that these frequencies are actually dominated by temperature. So the acceleration is evolving like temperature is evolving, and by the distortion of the whole structure of the GRS and the satellite. And we also noticed another thing, that is that we find some evidence that is compatible with a static pressure imbalance at the test mass location that is a part of a face of the test mass has a slight more pressure than the other one. Less than 1% is the difference. And this causes a static force that evolves with the pressure evolution. OK, so now I guess that the real question is, what is the origin of the 1/f noise? We analyzed many things. We analyzed some of the effects that we could decorrelate. For some of them, we had some additional telemetries on board, like magnetic fields, thermometers, etc. For others, we had dedicated experiment performed not during the noise run, but during the mission itself. And for some others, we have estimations that are also based on ground measurements, but also on measurements on board LISA Pathfinder. So now, not all of these are actually showing a contribution. Many of them we had to exclude. And so I will just talk about the main ones that we found. And we actually find that the major contribution that is known up to now is the contribution from the gain fluctuation in the actuation system. So the voltages that are applied to apply forces on the test mass may variate because of gain fluctuation that are uncorrelated among the electrodes. And this could cause noise. This noise that is here and is in power, it is up to the 40% of the total measured excess over the Brownian. And then there are some other things that are listed in this plot. For instance, the voltage, the ones that are related to electrostatics, that is fluctuation in the voltage and the random charging of the test mass. And this can be actually suppressed by keeping under control the test mass discharging and the DC voltages. And then there are some other more. And if we add them up, we found this plot. So we found that actually the fraction of the noise power measured by LISA Pathfinder in February 2017, the unmodeled noise power fraction is about 54%. That is these blue points. And this is the best estimate that we have right now. Then in the paper, that I was mentioning before, we also have some more analysis, some more discussion, let's say, discussion about what it can then be. And so if you're interested, there is the discussion on the paper about some other effect that could not be measured on flight, but had to be analyzed or even tested before LISA. So now I have a very last slide, because we talked about LISA Pathfinder, but we are moving on. Now we are moving on to LISA. And the thing is, what is the difference between the GRS of LISA Pathfinder and the GRS of LISA? These slides, I know it looks more like a poster than like an actual slide. But there are a few different things. There are many different things, actually. We're not just talking about the GRS. We are talking about forces. So we have to keep in mind that we have to control the forces that are generated in the spacecraft at all levels, not just the GRS level, because LISA is very different from LISA Pathfinder. The spacecraft is much more complex, is much heavier, and there are many sources that can induce force to the test mass from within the spacecraft and not just the GRS itself. By the way, I would go through some news in the LISA GRS with respect to LPF. The first one is, of course, that the actuation scheme will be different because there will be no forces applied along the x-axis of LISA, as you might know. And so the actuation scheme and the electronics might be different. It is different also because of new suppliers. It is different because of some things that were noticed on LISA Pathfinder and some inaccuracies that had to be taken into account in the analysis. And now that are known, they can also be corrected before launch in LISA. And actually another great difference is about the charge management system, because in LISA Pathfinder to discharge the test masses, UV mercury lamps were used, so they were switched on before the experimental runs and switched off before it. And the thing is that LISA will have UV LED like the units, so they will be switched on and off continuously during the science runs. There are also some schemes that see them synchronized with the injection for the sensing system, and this will allow to keep the test mass charge under control within the science runs and not just to control it before and after. There will be a difference in the gravitational balance, because actually the first thing is that the LISA spacecraft is much heavier than the LPF spacecraft. So the balance authority to be compensated is much larger. And the other thing is that LISA, in opposite to LPF, in LISA, things are not staying still. For instance, the MOSA, that is the moving optical subassembly, is actually moving. So the gravitational field to be compensated for is changing in time. And this is another challenge that is adding to the other ones. And the grabbing and positioning release mechanism is going to be improved, because in LISA Pathfinder it showed some things that were not exactly expected. The release velocity was not exactly directed along the x-axis, but it also was directed along some other directions. But the criticalities have been understood, and they will be corrected in LISA. There have been some talks also yesterday about this, and there will be posters. And then, of course, there are many other modifications that are related to also to the design, to the suppliers, to the structural design, all this kind of stuff that I didn't actually list here. And the GRS is now approaching its testing phase. You'll see the engineering models and the qualification models are going to be built in the next few years and are going to be tested. So many testings that have been done for LISA Pathfinder will be repeated, and some new tests that are different from LISA Pathfinder will be done, of course. And the construction of the flight models is expected to happen, let's say, in 2 symposia from now. And so this is actually what I wanted to say. Here there is a list of the many talks and posters. I hope that I listed them all, and that are here in the symposium that regard LISA Pathfinder and the GRS of LISA. And some of them actually took place yesterday, but I guess if you're interested, you can also find the recordings. So I will not go through all the conclusion. I would just say that the LISA Pathfinder showed that, LISA Pathfinder provided a remarkable heritage for LISA. And analyses are not over, not just for the acceleration that I talk about, but also about the interferometer, also about the magnetic fields. There are analyses that are still going on and still providing useful science. And of course, the GRS testing is underway, and we will see in the next years how it will perform and go. And thank you for your attention.
Thanks, Lorenzo, for this amazing technological overview. We have time for questions. First one over there.
This is amazing. How well characterized is the environment, the external noise environment in the LISA location compared to the Pathfinder location?
Okay, I see. Actually, it's. There are some differences, of course, because LISA Pathfinder was in L1, which is kind of well characterized because of other missions that are in that point. And LISA will not be in that point. Will be in another location, and. Actually, is still on the Earth orbit. So I'm not exactly the expert of this thing, but I guess that for instance the solar wind and that kind of stuff will be kind of similar. I mean, it's not completely on another orbit than Pathfinder, but I have to say that I'm not exactly the expert for this thing. Yes.
We have a question over there, and then here.
So. Two questions, but I'll jam them together about the stationarity of the noise. So for the Brownian noise, that was just a nice power law decay over time. LISA is going to live for much longer. Do you expect that power law to continue, or it must hit some floor eventually? And is there any speculation as to when it would hit that floor?
Okay, so going back to the slide is actually a bit complicated, so I will say. This is more a question that is related to the vacuum environment. So this could be analyzed from a vacuum perspective, and the thing is that if the source that is emitting the gas is not changing, that the slope is expected to go on in time. And if that source at a certain point, for instance, depletes, then other sources can, for instance, can be detected. So there is actually no expectation for it going on steadily for the 10 years of LISA, but maybe some other sources can
okay,
also.
and then for the low frequency noise, there was a noise level as a function of time for Pathfinder,
yes.
where you were talking about the stationarity, and around something like 400 days, it had a bit of an adventure. Was stuff happening to the spacecraft at that time? Were people poking at it, or was it just a high variance time in the noise level?
Yeah, I guess it was. I mean, it was not related to anything. You mean the variations in the 1/f noise, right? Yeah, and there were not actually things that were done on the spacecraft. Those were always only noise runs. So it was just kind of random fluctuations.
So in the very beautiful pressure versus time you showed, there were some discontinuities in the temperature. It jumped up, and then it came back, and then it jumped down a lot and came back.
Yes.
Were there events that caused those temperature changes, or are those understood?
Yeah. So, if no, I will not. There were some changes in the mean temperature in all the noise runs during the actual mission. That was in the first month of the mission. It was about 22 Celsius, 23 Celsius, 24 kind of. Then during the extension of the mission, the temperature was brought to 11 Celsius. And the reason for that was that the noise, the Brownian noise. Sorry.
I'm thinking about the plot that had all the various pressures decreasing.
Yes. It's I mean it's much behind in the presentation. Let's see if.
There.
This one. Okay.
Yeah.
So these fluctuations are about 1 Celsius degree variation, 2 Celsius variation,
But it goes
etc.
up suddenly
This one,
and
it is
comes down.
11 Celsius. It's 11 Celsius, and the reason for that was actually to analyze the Brownian noise.
Okay.
Because it was expected to go down when temperature was brought down.
Okay, let's thank Lorenzo again.
Thank you.